Welcome to the Biochemistry Clinic. And today I think we have another interesting puzzle to sort out. So there is a question that came through from our previous session on beta oxidation, and this has to do with the ATP yield in beta oxidation. How do you calculate the amount of ATP that could be produced from a given fatty acid after complete beta oxidation? So let's have a look at a sample question. Calculate the amount of ATP yield from complete oxidation of a 16-carbon fatty acid. So I got a quick example of the most common fatty acid in human being, which is palmitic acid. It has 16 carbon atoms. Now, there are a few things that you need to know before you start calculating the ATP yield. So quick reminders, from beta oxidation, we are getting the following. You are producing 1 FADH2, 1 NADH, and 1 acetyl-CoA from one complete round of beta oxidation. Please take note. So for each round of beta oxidation, this is what we stand to gain. 1 FADH2, 1 NADH, and 1 acetyl-CoA. Now we know clearly that all the three products of beta oxidation will definitely produce ATP at the end of it all. The FADH2 and NADH are important electron carriers in the electron transport chain, and they produce ATP equivalents. Acetyl-CoA also is channeled to the TCA cycle, where it is converted to ATP equivalents. Now, remember also that each cycle cleaves 2 carbon atoms from the long chain acetyl-CoA, which is the activated fatty acid. So the 2 carbon atoms are given out as acetyl-CoA, which is used to generate ATP in the TCA cycle. Now, so if you have a 16 carbon fatty acid, for each round you are chopping off 2 from the 16. So first round you chop 2 carbon atoms, which come out as acetyl-CoA, you remain with 14. So you continue cleaving 2 by 2 by 2 until you remain with only 2 carbon atoms, which also qualifies as acetyl-CoA molecule. So the number of rounds, the number of chains of beta oxidation largely depends on how many carbon atoms exist. So for instance, if you have a 16 carbon molecule, you expect a total of 7 complete rounds and a total of 8 acetyl-CoA molecules produced. And no, you are wondering why 7 rounds, but if you come to think of it, it's pretty much easy, because after round number 6, you will remain with 4 carbon atoms only. And when you cut the 4 carbon atoms remaining in the middle, you have two carbon molecules, which are acetyl-CoA molecules. And then it means you cannot have the 8th round of beta oxidation, because you would have actually completed the cycles for a 16 carbon molecule. So please remember that for acetyl-CoA molecules produced from 16 carbon molecule, you simply divide 16 by 2. That gives you 8 acetyl-CoA molecules. But the number of rounds required to completely oxidize the 16 carbon fatty acid is 8 minus 1, which is 7. Now, here is a bit of information that you need to recall. If we are now to convert this yield into ATP, we have to recall this. 1 FADH2 is equal to or equivalent to 1.5 ATP. 1 NADH is equivalent to 2.5 ATP, and 1 acetyl-CoA produces 10 ATP molecules or equivalent in the TCA cycle. So what this means is that for a 16 carbon molecule, you have 7 rounds, meaning you are producing 7 FADH2. So 7 multiplied by 1.5 gives you 10.5. You have 7 rounds producing 7 NADH. 7 times 2.5 gives you 17.5. And for acetyl-CoA, from the 7 rounds of beta oxidation, you are producing 8 acetyl-CoA. 1 acetyl-CoA per round and 2 for the last round of beta oxidation. So 8 times 10 gives 80 ATP equivalent. Therefore, when you add 10.5 plus 17.5 plus 80, you have a total of 108 ATP molecules produced from this 16 carbon fatty acid. But we have to recall that the process of activation from a fatty acid to an acetyl-CoA invests 2 ATP molecules. So the first step in beta oxidation is the activation, which occurs in the cytosol before the activated acetyl-CoA is transported via the carnitine shuttle into the mitochondria. So remember the 2 ATP molecules that you invested when you're activating the fatty acid at the beginning. So you subtract the ATP molecules that you used at the beginning of the cycle during activation. So 108 ATP minus 2 ATP used in the first step will give you approximately, well, exactly, not approximately, but exactly 106 ATP molecules. So basically, this is how you calculate the ATP yield from a given fatty acid, of course, with an even number of carbon atoms, unless there's any other question. Otherwise, thank you very much for watching.